Welcome back to next tutorial video. In last tutorial we have stopped at designing Butterworth filter. So we have chosen one circuit, that is this circuit, and the transfer function of this circuit is given as this equation, and from this equation we are having relation with the specifications like this. So I am continuing after this. We need to design two second order filter for first second order filter. We take two poles, that is P2, P3, which are that I have calculated earlier are minus omega naught minus 0.923 plus J 0.382 equal to 0.923 minus J 0.382. So these are the complex conjugate of filters. From that we are having Q1 equal to 0.541. Q1 we have derived equation earlier for Q1. So after finding Q1 we will have transfer function like this. H1s equal to minus 2 omega naught square upon s square plus omega naught Q1 s plus omega naught square. Here 2 is the DC gain. So for this second order filter we are taking DC gain equal to 2, and for the next filter we will also take DC gain equal to 2 to maintain the symmetrical gain across two cascade systems. From this circuit now we need to find out the values of RC components. So for simplicity let us assume RA equal to R1 equal to R2 equal to Rx, which will give Rn equal to Rx by 2. And from this circuit this is the R1 that I forgot. So this is the R1 value. Now let us have C1 equal to C equal to Cx. Assume Cx equal to 10 nanofarad. Now omega naught, that is 3 dB cutoff frequency, equal to 1 upon Rx Cx. Q1 equal to R upon Rx. So the Rx would have 4.58 kilo ohm, R equal to 2.48 kilo ohms, and Rn equal to 2.29 kilo ohms. These values I have calculated and I am just putting these values here. You can calculate it offline. So this is the first second order filter. Now second order filter we are taking poles P1 and P4. P1 is omega naught minus 0.382 plus j sine plus j 0.923. P4 is complex conjugate, that is omega naught minus 0.382 minus j 0.923. From here we will calculate Q2, that from the formula that we discussed earlier. Q2 will be 1.308. Again we will be making the same assumptions like RA equal to R1 R2 equal to Rx, and the DC gain is again 2, so Rn will be Rx by 2. Again assume C1 equal to C equal to Cx and Cx equal to 10 nanofarad, and we are having this equations. And but the Q1 here was 0.5 something, but Q2 here is 1.308. So there will be changes in values of R, that will be, so the Rx would be 4.58 kilo ohms, that is same with the earlier value. Rn equal to 2.29 kilo ohms and R equal to 5.99 kilo ohms. So these are the final values. Now finally we need to see what is the arrangement of filter. Final circuit. This I will be drawing in a small so that it will be covered in this page. This is 2.29 V in 2.48 10 nano 4.58 4.58 is also 4.58. Kilo nano farad. This is the first second order filter. We need to cascade it another second order, so I'll be writing like this. So from here we'll cascade like .29 . So this is the final filter. On the screen you will be noticing two parts, so I'll be covering like this. This is the first filter, then you will just cascade it and have it like this, and the output would be here VLP, output would be here VLP. The difference in values are here, like 5.99 and 2.48. These are because Q1 and Q2 are different. So this is the final realization of my fourth order Butterworth filter. So I have plotted this on a EDA tool and find out what is the transfer function, what is the magnitude response, what is the phase response of this filter, so that just to verify whether we have designed the correct filter or not. So this is the final plot of filter. So here you can see that the DC gain of the filter is 12.04 dB, that is close to 4, that we have assumed that 4 would be the filter DC gain, and here we are having this axis as omega. This is the magnitude response, this is the phase response. So at omega p equal to 20k, we are having 10.30 dB gain, that is approximately 2 dB down from our low frequency value. Why this is less than 2? Because we have over designed the filter. And similarly at the omega is equal to 50k, we are having response magnitude as minus 16.78 dB, that is approximately 28 dB down from the DC value, but in the specification we have targeted 24 dB, but since we have over designed the filter, it comes out to be 28 dB attenuation at 50k omega s. So from this plot we can say that we have achieved our specifications and we have designed a good filter which is maximally flat in pass band and attenuating in the stop band with our specification. So this problem ends here. So now moving to the next problem, that is based on diode circuit. That is a simple circuit, but just to have a quick insight into the diode system, I am introducing this problem. So the problem is, there is a circuit given. So this is the given circuit. In this circuit, there is a AC source which is having a 12 volt RMS value, and there is a battery which is charging from 12 volt to 14 volt from this AC source. So here we need to find out a part. Sketch the diode current waveform for VB equal to 12 volt. Then B part would be what are the peak and average value of current. And C part would be what do the peak and average diode current become when VB reaches volt. So this is our problem. Now going to A part. So A part is asking sketch the diode current waveform for VB equal to 12 volt. So first let's see, and there is one thing given in this circuit. Assume ideal diodes, rather ideal diode. So what is ideal diode characteristic? Which is like this. So this is VD, this is ID. So this is the line graph, which means if this is diode in forward bias condition, this will act as short circuit, and reverse bias condition, this will act as open. First, peak value of Vs, which is 12 root 2 equal to 16.97 volts. Now what is the peak current? Peak current equal to this 16.97 minus 12 upon 50 plus 10. So look at this circuit. So and we are assuming forward bias, so this will be short. Total resistance will be 50 plus 10, and battery is having as given VB equal to 12 volt. So the current would be given by this equation, that is 82.84 milliamperes. Now let us see when diode starts conducting. For that, boundary condition would be (16.97) sin omega t equal to 12. After this means when this value is greater than or equal to 12, the diode will start conducting because it will be forward bias. So from here we will get omega t equal to pi by 4. Now the input waveform is like this, input voltage waveform. Peak value is 12 root 2 and I am drawing the current waveform. So we are having this because since the diode start conducting after pi by 4, this is the omega t. So the current waveform would be this, and this value would be the peak value, and all others, in all other areas diode will be reverse biased, it will not be conducting. So this is the waveform of current. Now what is the average value? The average value is normal integration over period divided by the total period, pi by 4, 3 pi by 4, 12 root 2 sin theta minus 12 upon 60 d theta equal to 13.5 milliamperes. Similarly, when VB equal to 14 volt, peak current equal to 12, this is C part, current equal to 12 root 2 minus 14 upon 60 equal to 49.5 milliampere. Now the condition when condition for conduction, root 2 sin theta 2 equal to 14, sin theta 2 equal to 0.825, theta 2 equal to 55.6 degrees. So the average current equal to 1 upon 2 pi 55.6 into 180 minus 55.6 12 root 2 sin theta minus 14 upon 60 d theta equal to 6.2 milliamperes. this was our problem. So this simply illustrates the diode characteristics, and when we are assuming ideal diode, and assuming ideal diode, it shows the way to find out the problem solution. So today in this tutorial we have covered two problems. One problem with Butterworth filter design. It was having design of filter from specification given to realization of filter in terms of RC components. Then we have solved one simple diode problem assuming ideal diode characteristic. The same problem can be solved with different diode characteristics as given in, as taught in the class, which is constant voltage drop model and small signal model. So I am ending this tutorial here.